This video is meant to cover the conversation that I was intending to have in class on the relationship between mechanisms and rate laws for chemical reactions that we didn't have because we were out playing in the snow, except that the snow never actually came. But anyway, the first several slides are going to be, to a certain extent, review of things we've already talked about. And the main thing that I have tried to hammer into you over the course of chapter 14 is that you can't write the rate law for a reaction simply by looking at the balanced equation. You have to determine that experimentally. And so let me just go back through some examples of this that I actually were in a previous QOD. I've got three reactions here: the reaction of ammonium with nitrite to give nitrogen plus water, the reaction of tert-butyl chloride with water to give tert-butyl alcohol plus hydrogen chloride, and then the reaction of nitrogen dioxide with carbon monoxide to give nitrogen monoxide with carbon dioxide. The reason I picked these three is because they all have something in common, and that is they all have two reactants, and the stoichiometry of each of these is 1-to-1, right? One ammonium plus one nitrate, one tert-butyl chloride plus one water, one nitrogen dioxide plus one carbon monoxide. But what we find actually for these reactions is that they all have different rate laws. For the first one, it is first order in ammonium and first order in nitrite, which is the kind of most intuitive rate law that we can think of for that stoichiometry. But for the second one, the tert-butyl chloride plus water, it turns out to be first order in tert-butyl chloride, but zero order in water. And then finally, for the third one, nitrogen dioxide plus carbon monoxide, it turns out to be zero order in carbon monoxide, but second order in nitrogen dioxide, which runs counter to something I mentioned in class, which is that the coefficient of a particular thing in the balanced equation sort of provides the upper limit for its reaction order. But that turns out not to be true all the time. And this is an example of that. So what's going on here? You've got three reactions in which you've got identical stoichiometry, but three different rate laws. Well, what we've said is that this must be the case because these reactions are proceeding through different mechanisms. And so mechanisms, as we've said in class, just to remind you, most balanced reactions that we write don't occur in a single step. That is, they don't occur just by two or three things colliding together all at once and it's all over. Some things have extremely complex mechanisms. But in general, and we're not going to talk about things that have super complex mechanisms, but most chemical reactions require at least two elementary steps, and some require even more. And that series of elementary steps that add up to the overall reaction is called the reaction mechanism. And again, we're still reviewing right now. And so let's think about a reaction in which A plus B gives me C plus D. Well, it's possible that the mechanism of that reaction could just be a molecule of A collides with a molecule of B, and that produces a molecule of C and a molecule of D. And therefore, it would be a single-step mechanism, and the overall balanced equation would represent the mechanism. That's a possibility, and there are reactions like that. Let's just look at a different mechanism. Here is an example where I'm taking reactant A, and it is just spontaneously isomerizing to intermediate E. Then intermediate E reacts with a molecule of B to give me a molecule of C plus a molecule of D. So that's another mechanism that would give us the same overall reaction, right? The intermediate cancels. A plus B gives me C plus D. So that's another possible mechanism. Here's another one. Two molecules of A react to give me some intermediate E plus product C. Intermediate E reacts with a molecule of B to give me product D, interestingly, and regenerating A. So here's an example in which A is reacting not only as a reactant, but also as a catalyst, right? Because one molecule of A ends up getting regenerated in the end. But then if you add this whole thing up, 1A would cancel that A, E would cancel E, and you'd have A plus B gives you C plus D. So there's another mechanism that would give you the same overall reaction. Here's another one. A decomposes into E plus F. Intermediate E reacts with the molecule of B to give some other intermediate G. Now F and G react together to form C plus D. E, F, and G are all intermediates that are formed and then consumed. If you add this all up, you'd get A plus B gives you C plus D. And I could write more. So what I've done here is I've given you 4 possible mechanisms that would all give you that would all add up to A plus B gives you C plus D. Okay, the other thing that we've talked about in class is that although the rate law for the overall reaction cannot be written from the balanced equation, the rate law for an elementary step can be written from the balanced elementary step. And so if we have an elementary step in which is unimolecular, which is simply a single molecule of a reactant goes to products, we can write the rate law for that step based on what we call the molecularity of the elementary step. That is a single reactant. Therefore, it's going to be first order in that reactant. I could have 2 different possibilities of a bimolecular reaction in which 2 molecules of A give me products. In that case, the rate law for that elementary step would be K times A squared, corresponding to the molecularity of the reaction. Or I could have A plus B going to products, in which the rate law for that elementary step would be first order in A, first order in B. Termolecular elementary steps, although you see 3 examples of them here, and there are 3 possibilities, right? 3 molecules of A giving me product, 2 molecules of A plus a molecule of B giving me product, a molecule of A plus a molecule of B plus a molecule of C giving me products. I'm not going to teach you anything about termolecular elementary steps because I personally don't know any, and there are no examples in the textbook that talk about a termolecular step. I think they do exist, but they're rare, and we're not going to cover them. All right, well, let's try and bring all this together. And so we've talked about the fact, okay, there are many different possible mechanisms we could use to write the same reaction. We do know that for a elementary step in a mechanism, we can write the rate law for that step based on its molecularity, based on the balanced equation for that step. How does this get us to the end, to its relationship with rate laws? Well, let me remind you, here's a typical reaction energy diagram that we've talked about in class, and that is, here are the reactants over here. Now, this is for a particular reaction, but we can think about this generically. We've got the reactants over here, we got the products over there, and we have the transition state here, which this is called the activated complex, which is another name for the transition state. And we talked about the fact there are 2 different energies here, right? This delta E, which I would call delta G, is simply the overall reaction energy for the reaction. It determines whether it's endothermic or exothermic, or endergonic or exergonic. It's this height of the activation energy barrier that has to do with the rate. That's nice, but it turns out that this is really only the reaction energy diagram for a single step in a reaction, or for a single step, or for a reaction that has a single step mechanism. If you've got more than one step in your mechanism, you're not going to have a reaction energy diagram that looks like that. You're going to have a reaction energy diagram that looks like this, or that looks like this, right? So here is an example of what could be a reaction energy diagram for a 2-step reaction. Each step has its own reactants and products and its own transition state. The product of the first step is the intermediate, because then it goes on and gets consumed in the second step to give you products. So this is a possible reaction energy diagram for a 2-step reaction. In this case, the overall reaction is endergonic. It doesn't have to be, it just happens to be in this particular diagram. And it happens to be in this particular diagram that the transition state for the first step is higher than the transition state for the second. But that doesn't necessarily need to be the case either. The point is that this is an example. If you have a 2-step reaction, it's going to have 2 transition states and some intermediate spot in between. And this would be what could be a possible reaction energy diagram for a 3-step reaction. Now you've got 3 transition states and you've got 2 intermediate points. Again, this is endothermic overall. It doesn't necessarily have to be the case that all 3-step reaction mechanisms are endothermic. It just happens to be that this example that they've shown, and I just took these are just photographs out of your textbook, that in each case it turned out to be endothermic. Okay, what's the bottom line? If you have a multi-step mechanism, the slowest step in that mechanism is going to be the step with the highest energy transition state. That is, the highest mountain in the mountain range, the highest peak in the mountain range that you have to go over is the transition state for the slowest step. So for this particular one, because this transition state is higher in energy than that transition state, the first step would be the slowest step. For this reaction, in which the second transition state, the transition state for the second step is the highest, the second step in this particular mechanism would be the slowest step. We call that the rate determining step because, and here's the really important thing, the rate law for the rate determining step is going to be the rate law for the whole reaction. That is, the slowest step is going to determine the rate for the entire reaction, and therefore the rate law for that reaction, for that step, is going to be the rate law for the whole reaction. Now, just as a reminder, I've drawn once, I think, on the board, my funky looking hourglass concept, in which I've got an hourglass that has two constrictions, one of which is narrower than the other. And whether I put the narrower constriction at the top, therefore, and that would be analogous to a reaction in which the first step is slower than the second, or whether I put the narrower constriction below, that would be analogous to a reaction mechanism in which the second step is slower than the first. The rate at which the sand hits the bottom is going to be the rate at which it goes through the narrowest constriction, regardless of whether that's first or second. And the textbook uses the concept of the toll plazas. You've got two toll plazas. If these people are not as good at taking people's tolls, not as fast as taking tolls as these people are, you're going to get a backup at the first toll plaza, and you're not going to get any backup here because cars are actually arriving here at a slower rate than they can be processed. And so the flip side would be that you've got a fast group of people at toll plaza A and a slow group of toll takers at toll plaza B. Regardless of which is the case, the rate at which cars are getting to the destination is going to be the rate at which they go through the slower toll plaza. And so just a reminder from what I said from the previous slide, the rate law for the rate determining step is the rate law for the whole reaction. Well, this finally gets us to where we can connect mechanism with rate law. And let's take a look at some examples. This is one that I've had on the board a couple different times. It's the reaction of tert butyl chloride. And I mentioned that we've talked about two different isomers that have the formula C4H9CO. One of them is called tert butyl chloride. The other one's called N-butyl chloride. And I'll do that one next. They have different rate laws, and that's because they have different mechanisms. So let's start with tert butyl chloride first. Here's the overall reaction. It turns out that this is the mechanism. It's a three-step mechanism. In the first step, tert butyl chloride decomposes into what's called a tert butyl cation and a chloride anion. In the next step, the tert butyl cation reacts with water to give this new cation, in which is simply a combination reaction of the tert butyl cation plus water, but it is also charged. Then that what's called an oxonium ion reacts with chloride to give tert butyl alcohol, which is the product, plus hydrogen chloride, which is the other product. This intermediate cancels out that intermediate, this intermediate cancels out that intermediate. It all adds up to the balanced overall equation. Now, when it comes to transition states and what's the rate determining step, it turns out that the first step is the slow step. Therefore, the first step is rate determining. Therefore, the rate law for the first step is going to be the rate law for the entire reaction. And so the rate law for the first step, the slow step, is simply because it's just unimolecular, one molecule of tert butyl chloride. The rate for the first step is going to be K times the concentration of tert butyl chloride. And because that's the slow step, then that's the rate law for the entire reaction. And that is in fact what we observe when we run this reaction and change various concentrations of terbutyl chloride in water. It is first order in terbutyl chloride and zero order in water. Well, let's move on to the other version of this reaction, in which instead of having terbutyl chloride, we have N-butyl chloride. Okay, that proceeds through a different mechanism. The first step, rather than being just a decomposition step of, as it was with the terbutyl chloride, in this case, N-butyl chloride reacts with water to give, again, this what's called an oxonium ion and the chloride, and then the oxonium and the chloride then react to form the terbutyl alcohol plus the hydrogen chloride. In this case, it is again, in this particular mechanism, which is now 2 steps instead of 3, it's again the case that the first step is slow. Therefore, I can write the rate law for the first step. It is going to be K times the N-butyl chloride plus times the water. And because that's the slow step, then that is the rate law for the entire reaction. And indeed, when we run this reaction and do rate law studies, that's the rate law we observe. Let's look at one more example, which is this reaction of nitrogen dioxide with carbon monoxide to give nitrogen monoxide or nitric oxide plus carbon dioxide. This turns out to be a 2-step mechanism as well. Interestingly, what happens in the first step is that 2 molecules of nitrogen dioxide get together to give 1 molecule of nitric oxide plus this intermediate nitrogen trioxide. Nitrogen trioxide then quickly reacts with a molecule of carbon monoxide to give you carbon dioxide plus nitrogen dioxide. What you'll notice in this case is we've got an example of nitrogen dioxide acting as both a reactant and a catalyst. 1 molecule goes through the reaction, the other molecule gets regenerated in the end, but it adds up to the overall reaction. In this case, once more, the first step is slow. The first step is rate determining, and therefore we can write the rate law for the first step, which is going to be the rate law for the whole reaction based on the molecularity of the first step. And this is the observed rate law for the entire reaction. Now, up to this point, I keep showing you examples in which the first step is slow. What would happen if the first step was not slow? Well, let's just look at one example of this, and this takes a little bit more complex thinking in math, and I'm not going to sit on this for too long. But here's the reaction in which 2 molecules of nitric oxide plus bromine give you 2 molecules of NOBr. I think it's called nitrosyl bromide, but I wouldn't stake my life on it. Okay, this is a 2-step reaction. In this reaction, 1 molecule of nitric oxide plus bromine gives you this intermediate NOBr2. Then that intermediate NOBr2 collides with another molecule of nitric oxide to give you the 2 product molecules. This turns out to be an intermediate that cancels out. When you're done, you get 2NO plus Br gives you 2NOBr. Now, in this case, it turns out that the second step is slow. And therefore, the rate law for the whole reaction is going to be the rate law for the second step. And I can write the rate law for the second step, and there it is. The problem here is that NOBr2 is not a reactant in the overall equation. And so how can we write a rate law for this thing based on the reactants? Well, without belaboring the point, I'm simply going to tell you that the concentration of NOBr2 is going to be dependent on the concentration of the 2 things that reacted to make it. And so essentially we can substitute in the concentrations of these 2 items for the concentration of NOBr2. When I do that, when I substitute those 2 in for this, I get this equation, which I can then simplify simply as the rate is equal to K times NO squared times Br2. And so if you have an instance in which the second step is slow, then it turns out you're basically adding up how many total molecules of reactants are you having to use to get to this rate determining transition state, which would be represented by that arrow. And that would be your rate law. Okay, I've gone longer than I probably intended to. one quick comment. Can you prove a mechanism by the rate law, by the overall rate law for the reaction? And the answer to that is no. You cannot prove a mechanism. I could write other mechanisms for this reaction that would give me this same overall rate law. What an observed rate law can do is rule out a proposed mechanism. If I write a mechanism for this that is inconsistent with this rate law, then that's not a plausible mechanism. But there are multiple mechanisms that I could propose that could be consistent with this rate law. So the actual observed rate law cannot unequivocally confirm what the mechanism is, but it can rule out some proposed mechanisms. Okay, that's the end of the video. The homework assignment should not be too difficult for you.